Hello from ChemHelp ASAP. This video is a review of many bases that students see during a 2-semester sequence of Organic Chemistry 1 and Organic Chemistry 2. Because bases are inevitably linked to acids, we'll discuss some acids too. The list of bases covered in this video is not complete, but it should provide a decent review of what most students will see and remember in organic classes. If I left out your favorite base or your instructor's favorite, let me know in the comments section and maybe I will make a follow-up video. Finally, this video is intended to be a review and is recommended for students who already have learned some organic chemistry as opposed to beginners to the subject. When a chemist calls a reagent a base, then you know exactly what the role of that reagent is. It will deprotonate something. It might do other things as well, but bases deprotonate. Deprotonation involves the removal of a hydrogen, a proton. So if you have a base, your first action will likely be identifying which hydrogen is the most acidic and most likely to be removed by the base. In order to remove a proton, bases need to have some source of electron density. Normally that means the base is obviously electron rich, with an atom that is negatively charged, an anion. With lone pairs. These are normally stronger bases. Sometimes the basic atom is neutral, but still has a lone pair of electrons. Rarely, a really weak base may react as a base through using a bonding pair of electrons, especially a pi bond, as the source of electron density. Let's talk about how bases are often used. I think of bases as doing two things. One, they initiate reactions through deprotonation. So the first step is a deprotonation. This normally happens with strong bases. Strong bases are strong because they are highly reactive, unstable. By removing a proton from another reagent, the base transfers its reactivity and instability to the other reagent. That step, the transfer, is the event that starts the chemical reaction. The second thing that bases often do is deprotonate an acidic intermediate at the end of a reaction. This is a reaction quench and normally involves weaker bases. The reaction is over, but there's still some reactive acid floating around. The weak base deprotonates this intermediate, neutralizes the acidity, and puts an end to the reaction process. Let's talk a bit about language. Bases deprotonate. Bases remove a proton. Students often say, and I do too on occasion, that bases attack a proton. If possible, avoid saying attack when referring to bases. Attack is more often reserved for nucleophiles. Now this brings up an interesting issue. We identify bases because they are electron rich. Nucleophiles are also electron rich. Is it possible for a reagent to behave both as a base, because it is electron rich, and a nucleophile, again because it is electron rich? Here's an example. NaOH can react as a base with a ketone. NaOH can deprotonate, the verb for a base, the alpha carbon and make an enolate. NaOH can also react as a nucleophile with a ketone. NaOH can attack, the verb for a nucleophile, the carbonyl carbon and form a tetrahedral intermediate. Often a key aspect of using bases in organic chemistry is the proper selection of a base that behaves predominantly as a base and not a nucleophile in a particular reaction. Okay, let's talk about some specific bases. We'll start by discussing bases in the E2 reaction. At the top of the slide is an E2 reaction. The beta hydrogen of an alkyl halide is removed by a base, B-, and simultaneously the electrons in the CH bond form a CC pi bond and the halogen is ejected as a halide. Everything happens in one step. The beta hydrogen does not look particularly acidic. It's not. So the base needs to be very strong. Typical bases for the E2 reaction include hydroxide, KOH or NaOH, and the alkoxides, sodium methoxide, ethoxide, or t-butoxide. All of these are similarly strong bases and essentially interchangeable. One exception is t-butoxide. First, t-butoxide is most often used as a potassium salt instead of sodium salt. 2, t-butoxide is bulkier than the other alkoxides and can change the regiochemical outcome of the reaction, Zaitsev versus Hofmann product. So t-butoxide prefers to remove a less hindered beta hydrogen if available. Rarely you might see an amine like triethylamine being used as a base in an E2, but alkoxides are the classic bases for the E2. How do you make alkoxides? Well, normally you deprotonate the corresponding alcohol with a very strong base. To make a strong base like an alkoxide, you need an even stronger base. For this deprotonation, the classic base is sodium hydride, NaH. The base is H- hydride. Note that you can't use something like sodium hydroxide because the equilibrium for this reaction will not strongly favor the alkoxide. To favor the alkoxide, your desired product, you need sodium hydride. As useful as sodium hydride is in this reaction, you normally do not see sodium hydride used in many other reactions. Let's see some more strong bases that are used in other reactions. Another reaction that requires a very strong base is the deprotonation of terminal alkynes to make acetylides. Is NaOH strong enough? No. Is sodium hydride strong enough? No. You need something stronger. You need sodium amide, NaNH2. This base might resemble sodium hydride, NaH. They do look a bit similar, but they are very different. NaH is a source of H- hydride. NaNH2 is a source of a nitrogen anion. Sodium amide is stronger and what is often used to make acetylides, especially when deprotonating acetylene. Our next strong base is LDA, lithium diisopropylamide. LDA is the base that traditionally is used to cleanly make enolates. So we are deprotonating an alpha proton of a carbonyl. Most often, the carbonyl will be a ketone, but it could be an ester or amide as well. Like NaNH2, LDA is a source of a nitrogen anion. It's really basic. Note that while NaNH2 is basic enough to make an enolate, it's also nucleophilic and tends to attack the carbonyl instead of doing the deprotonation. LDA, with its two bulky isopropyl groups, is less likely to attack and more likely to deprotonate. Is LDA the only base that can make an enolate? No, you can also use weaker bases like sodium hydroxide and sodium methoxide. A key difference is that deprotonation with LDA is essentially irreversible, with nearly 100% enolate formation. With sodium hydroxide, the deprotonation generates far less than 1% of the possible enolate. Note that depending on the reaction, 1% enolate may be adequate to initiate the reaction. Regardless, if you want to completely form an enolate, do use LDA as the base. There are other strong bases, some even stronger than LDA, but we've now covered the most important strong bases. Let's now look at just a few weaker bases. Amines, which include mostly alkyl amines like triethylamine, and aromatic ring nitrogen compounds, namely pyridine, are weaker bases. As has been mentioned before, triethylamine can occasionally be used as a base for some E2 reactions. Alkylamines and compounds like pyridine, however, are more often encountered as weak bases for neutralization of any strong acids that are formed in a reaction. An example is shown on the screen, the reaction of an alcohol with tosyl chloride to make a tosylate leaving group. The reaction is often performed with pyridine in the reaction or even with pyridine as the reaction solvent. In this reaction, HCl is formed as a side product. HCl can react with many functional groups, so neutralization of the HCl with pyridine is necessary to prevent unwanted side reactions. Amines like triethylamine give much the same result. Water and alcohol solvents are both examples of very weak bases that often play an important role in acid-catalyzed reactions. For example, in the acidic hydrolysis of esters in water, this reaction has multiple mechanistic steps with several protonation and deprotonation steps. Here in the middle is an intermediate along the reaction pathway. This intermediate needs to be deprotonated to continue the reaction, and that requires a base. The reagents of the reaction, however, do not include a strong base like sodium hydroxide. Instead, the solvent, which is water, though only very weakly basic, is basic enough to accept the proton and allow the reaction to progress. Water and alcohols often serve as weak bases for acid-catalyzed reactions. The final base I want to discuss is the mysterious B, just a neutral B with a lone pair. I use B as a base in my classes for certain situations. Note that your instructor may not, so follow your instructor's wishes. In a fairly small number of reactions, the conditions are very strongly acidic and do not include an obvious base, not even a weak one, from among the reagents or solvent. In these reactions, you sometimes need a base to remove a proton during the mechanism. In these cases, something must be serving as the base. I call that base B with a lone pair. What are these reactions? Two are shown. The E1 reaction of an alcohol ultimately gives a carbocation, and the last step is loss of a beta hydrogen to form an alkene. What is the base that removes this proton? You don't have an obvious base among the reagents, so I just use B. In an electrophilic aromatic substitution, you form a positively charged ring, also a carbocation, that needs to lose a hydrogen to restore aromaticity. There is no base in the reagents. Let's just use B. The use of B is uncommon and mostly restricted to reactions that are strongly acidic and lack a solvent that can act as a weak base. Note that B is not a real reagent. You can't go into a lab and find a bottle of B. It is a placeholder that acknowledges that the mechanism does require a base, but there's not an obvious reagent that serves that role. That was a short review of bases in Organic 1 and Organic 2. Thank you for watching until the end. Please leave a comment, leave a like, or subscribe to the channel. Take care.